Oh, in this lesson we're going to be talking about 4-4, which is counting. Fifth objective is to find the total number of outcomes in a sequence of events using the fundamental counting rule. In a sequence of events, in which the first one has a one ability to K2, and the third has K3 possibilities, and so forth and so forth. The total number of possibilities of the sequence will be the product of the number of possibilities. The biggest one they always go with, like Subway. Like Subway, you have like three breads to choose from, three cheeses to choose from, maybe like 10 vegetables to choose from. So if you want to know all the combinations that you could possibly make, you would multiply all those up, and that would tell you how much is there are. I'm sure there's more than that because you got sauces and seasons, and I was just guessing. I really don't know how we have for Subway. So again, that word and. Sorry about that, guys. I'm just having some technical difficulties. We'll fix it. All right, so let's look at example 20. Or not. What just happened? Here we go. Example 20. How many different hats are there? So we have a yarn shop that has patterns in 4 styles with 5 stitch options, 3 sizes, 8 yarns that are appropriate for the hat. How many different hats can be made, and how many hats can be made by size is disregarded. So we're not going to pay attention to like medium, small, large, things like that. So to figure this out, just like I was showing earlier, just have all the options. So your K1 here, you have 4 different styles. K2 would be there's 5 different stitches. K3 would be there's 3 different sizes, and sorry, 8 yards. So how many different hats can be made? You would literally go 4 times 5 times 3 times 8. There is 480 different hats that can be made. If we do disregard size, then we would just have 4 times 5 times 3, which is what, 20 times 3, which is 60 different hats that can be made. Oh, I lied because I'm disregarding the size, so it actually be 4 times 5 times 8 for the yarn, with the wrong number there. All right, so that'd be 20 times 8, which is 160 different hats that can be made, not counting the sizes. So in the next example, the sample space for each event will be the same. However, in one case, repetition is allowed, while in the other case, repetition is not allowed. So depending if I can repeat an option or not repeat will depend on how many options I actually have. So for instance, if I was to put this piece of lettuce here, would more lettuce on it? Sandwich case. And we want to talk about the lottery game. Lottery game. All right, so a lottery game called Pick Four is played by picking 4 digits, 0 through 9. How many sets of 4 digits are possible if digits can be repeated? How many sets of 4 digits are possible if digits cannot be repeated? So you got to think of it like this. So if I have 10 numbers, that's 0 through 9, that's 10 numbers, and it can repeat. That means I would have 10 the first time, 10 the second time, 10 the third time, and 10 the fourth time. So basically, it doesn't affect or influence the next pick. So I can have 1, 1, 1, 1 if I want it to. And when I do that, 10 to the fourth power basically here is just 10,000, 100,000, 10,000. It's got me second guessing myself. 10 times, yeah, 10,000 options. So if digits cannot be repeated, then the first pick has 10 options, but then the second will have 9, then 8, and 7. So therefore we have 10, 9, 8, 7, which comes out to be 5,040. So you can see that if I play a lottery game and I let numbers repeat, now there's 10,000 different combinations. So you have a 1 out of 10,000 of getting that lottery money. Versus if I limit it to now, all right, if that number gets chosen, it can't be chosen no more. Now I only have half that many possibilities. So then your chances of winning has now doubled, even though 1 out of 5,040 is still not huge compared to how many people play the lottery, could be pretty effective on if you play the game or not. All right, so let's talk about factorial formulas. If you've never heard the word factorial, it's a thing with an explanation point. So for any counting number in factorial, that's what this guy right here is. That is a factorial right here. Just means you're going to take this number times its the next number minus 1 minus 1. So for example, 5 factorial would be 5, minus 1 would be 4, minus 1 would be 3, minus 1 would be 2, minus 1 would be 1. You stop at 1, you don't go to 0. Notice here it stopped at 1. Also, a thing to note, 0 factorial is 1. There is a math formula that we can prove this, or you can just take my word for it. So therefore, 5 factorial would be 120. So this comes in handy if something like the lottery ticket says, hey, there we have 10 numbers. You get to choose the 10 numbers in any way. How many options do you have? So you would do 10 factorial and then be 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. So instead of multiplying this out, I can just state this, then go find the answer. So in our sixth objective here, we're going to find the number of ways that our objects can be selected from n objects using what we call the permutation rule. So a permutation is an arrangement of n objects in a specific order. So that means permutation order matters, right? So first consider the instance where n objects are different. So when all objects are used, then the permutation of n objects in a time is written as npn and calculated by npn in factorial. Does this notation purposes. Here's what you need to know. So permutation rule number 1, when R of the n objects are used in a specific order, the permutation of n objects R at a time is NPR. That's just notation, but this is the formula. So this will be n factorial divided by n minus R factorial. So if I'm trying to find the permutation of 5 things happening, and there's 32 events, I would then do 5 factorial over 32 minus 5 factorial and get my conclusion of how many different combinations of these events I could have. And 5 events out of 32. If I can't repeat, in order matters. So if I do it first, I can't do it second. So let's look at an example using that. I think I can keep this up. Yeah, probably a little bit. It's going to look a little weird for y'all. I'm going to keep this up on my page. So when I do A, I'll do B over here in the corner, but you would just continue down in your notes just so that we can keep this formula here. So example 22, ways to visit patients. So in part A, suppose a home nurse has 6 patients that must be visited in one day. How many different ways can the nurse visit them? Then part B, if the nurse must choose 4 to visit in one day, how many ways can they choose? So in part A, if all 6 patients must be visited, there are 6 patients that can be visited first, then 5 can be visited second, then 4, and so forth and so forth. So I can literally just do 6 factorial. So that's 6 times 5 times 4 times 3 times 2 times 1. So there is 700 and different combinations of seeing these 6 patients. Again, where this one is all of them had to be applied. In part B, it says if the nurse must choose 4 to visit in one day, how many ways to choose now? So this 4 is now my N, and this 6 is now my R. Oh, I got that backwards. I got that backwards. In your total sample. So there's 6 in the sample, but I want to only choose 4. So this would be my R, this would be my N. So when I plug it in, I would get 6 factorial over 6 minus 4 factorial. So that ends up being 6 factorial over 2 factorial. Now, what's really cool about this is remembering what these things are. So 6 times 5 times 4 times 3 times 2 times 1 over 2 times 1, I really just have 6 times 5 times 4 times 3. So I can simplify my answer, 6 times 5 times 4 times 3, and I get 360 combinations to choose from if I only need to see 4 of my 6 patients. All right. So that's how you could use the permutation rule formula. So again, that would be the result there. So let's now consider some of the objects being identical. So that was 6 unique patients. What happens if some of the options look exactly the same? So in the permutation number 2 rule, the arrangement of n objects in a specific order using R1 objects as the identical R2 objects are identified as RP objects identical, etc., etc. I can now do n factorial divided by however many options there are for the first one factorial times however many options there are for the second factorial times how many options for the next one, and so on and so on. Knowing that each of the options for all the options I have all equal up to the total amount. So think of it like this. We are determining the frequency of how many times each option is used. So when we look at this example, this will make sense here on 23. How many permutations of the letters can be made from the word Mississippi? Permutation means order matters. So if I use one letter, I can't use it again. So we see that there are 11 letters in Mississippi, and then I need to know the frequency. So I see I have one M, 4 I's, 4 S's, and 2 P's. So thus the number of permutations can be made as such. So using this formula, I have 11 factorial divided by, all right, 1 factorial for my M times 4 factorial for my I's times 4 factorial for my S's times 2 factorial for my P's. Now, I'm going to show you real quick on how you can just type this into the calculator as well. So let me switch to my calculator real quick. Make sure y'all can see it. All right, perfect. So if you just do control divide, that gives us a fraction. Then do 11. To do factorials, where's my little arrow? If you, oh, that's not it. Hold on. Which is that? Oh, it's over here by the G. All right, so if you go to G, you'll find the exploitation point right there. So that's going to be 11 factorial. And then now I'll do 1 factorial times 4 factorial times 4 factorial times 2 factorial, and I get that. So I would get then a total. So let's switch back. I would get a total of 34,650 different combinations of rearranging the word Mississippi where order matters. So again, meaning if I use one word letter, I can't use it again. All right, so now let's move into our seventh objective. Our seventh objective says find the number of ways that our objects can be selected from n objects without regard to order. This is called the combination rule. So a combination is a selection of distinct objects without regard of order. So if I want to use it first, I can use it first. I can use it third, fourth, fifth. I can repeat it as many times as I want. It really doesn't matter to me. On the order that it's used. So combinations are used when the order of arrangement is not important, as in the selecting process. Suppose a committee of five members is to be selected from an organization membership of 45. The five selected committee members represent a combination, meaning combination. If I have 45 people in a group and I need to select five of them, if I'm the first person in the group or the last person in the group, I'm still in the group and the order is not going to matter. Versus, again, going back to those patients, if I see him first, I can't see him any other time. But if I can be selected first, or I can be selected fifth, or I can be selected in the middle, but I can be selected at any point and still be part of the combination. So the combination rule, what you need to know for our objects selected from n objects is denoted by NCR and is given by this formula right here. It looks just like permutation. The only thing that gets added is also multiplying by the however many options you want, factorial. All right, so let's practice applying this. The biggest part you're going to have issues with is you just got to find out which one is a combination and a permutation, meaning how do I select the people they want me to select or objects, and does the order matter? If I choose it first, is it going to affect the rest, or can I choose it first or fifth? So let's look at example 24 using that formula on your page. So this one says how many different tables of 4, so this will be my R, can you make from 12 potential bridge players? So this is N. So if I group them up, it's not going to matter how they got grouped up. If they're first, second, third, or fourth, they're still going to be in that group. So I can see here that order doesn't matter. So this is a combination. So the question asks how many different groups of 4 players can be selected from 12 potential bridge players? This will be a combination. So that's what we got to do first. Determine if it's a combination or a permutation. I see that my N is 12, my R is 4, so therefore this is the notation they use, but it's going to be the 12 factorial divided by 12 minus 4 factorial times the 4 factorial. So that's that extra step in the combination formula. And again, I'm just going to go back to my calculator to perform this. So that's going to be 12 factorial, 12 minus 4 times 4 factorial. You do not have to put multiplication. I don't know why I did that. I had multiplication symbols in between my exclamation points and wasn't getting my answer. So therefore, there are 495 possible different bridge outcomes if I have a group of 12 and I want to put them in groups of 4. All right, let's look at example 12 there. Groups of presents. If a person can pick 3 presents, so that's my R, from 12 presents, that's my N, under a Christmas tree, how many different groups of presents can there be? So it looks like if I select the present the first time, or the second, or the third time, it doesn't matter. It will still be one of my 3 presents. So in this case, the solution, again, this tells me is a combination. So again, that's the first thing I want to determine. And then I'll do 12 factorial over 12 minus 3 factorial times 3 factorial. So this ends up being 12 factorial over 9 factorial times 3 factorial. I'm going to try to simplify this up a little bit. 9 factorial into 12. I can do 12, 11, 10, and then this 9 through 1 would eliminate the 9 factorial. And on the bottom, I would have 3 times 2 times 1. Again, you can just type this in the calculator, but it's always fun to simplify. 3 goes into 12 4 times. 2 goes into 4 2 times. And then I don't really need the 1. So 2 times 11 is 22. 22 times 10 is 220. Again, you're more welcome to plug it into the calculator. But it's always fun, in my opinion, just to do it by hand. All right, but that will conclude this topic. There's only one more topic left, and I'll see you in that next video.